Hi, I'm Marcello, and I work in the AndroidX architecture components team at Google. Today, we'll be discussing the conversion of the Lifecycle libraries to KMP. Before we start, let's set expectations. This talk is designed for library authors that would like to migrate their libraries from Java or Kotlin to Kotlin Multiplatform. If you're an app developer, the talk can still be useful for you to learn more about what it takes to convert a library to KMP, the API challenge we faced, and how the process went. Let's first take a look at our agenda today. We will first talk about the Android support for Kotlin Multiplatform. Second, we will briefly discuss the timeline to get the Lifecycle Multiplatform to stable. Third, we will deep dive in the API challenge we face and how we overcame them. This is going to be the longest part of the talk, covering API decisions and issues we found. On Google I/O 2017, we introduced the architecture components libraries. Those libraries were built for Java first ecosystem and for the Android UI toolkit based in XML and views. Fast forward to Google I/O 2024, now we have a Kotlin first ecosystem and we have the modern UI toolkit for Android, Compose. And we have announced Kotlin Multiplatform support for Android officially. But what does that mean? Basically, we need to explain the two different types of support, KMP compatibility and KMP support. KMP compatibility is when we take a library, such as a Lifecycle, and we make it available to be used in the common source set of a KMP project. It might require integrations, such as implementing your own Lifecycle owner or using a library that does that for you. For example, Navigation Compose Multiplatform provided by JetBrains. Now, KMP support is like a KMP compatibility, but integration is provided for you. You can just drop the library in your project and everything works out of the box. An example is the Run library. It's still unclear which library should reach each level of support, and we are still learning what works best here. Now, let's talk about the timeline to get Lifecycle KMP to stable release. The initiative spanned from January to May 2024, the main goal being the conversion of navigation to KMP. We partnered with JetBrains from the beginning, and they were enthusiastic about enabling KMP support for Navigation Compose. From our side, we focused on unblocking that work. We mapped the dependencies that navigation requires and convert them to KMP. On their side, they focused on getting the Navigation Compose artifact convert to KMP. Most importantly, it was necessary to get the Lifecycle KMP stable released before Navigation KMP was shipped. That is because of API stability. It ensures that all APIs that navigation requires are stable and will maintain binary compatibility in the long term. Finally, let's dive deeper into the API challenge we faced. If you have been doing Android development for a while, you are probably familiar with the lifecycle events: on resume, on pause, and so on. As it seems, the other platforms have very similar callbacks that can be translated almost one-to-one with the lifecycle events we have. Let's take a look at the iOS. Did become active is mapped to on resume, and will resign active can be mapped to on pause. That's also true for desktop. Windows gained focus can be mapped to on resume, Windows lost focus to on pause. Finally, the web has a much simpler lifecycle mapping. Focus goes to on resume, and blue is mapped to on pause. So let's talk about the ViewModel provider. The ViewModel provider is the main API surface for the ViewModel library, but you might not have used it directly. That is because we provide high-level APIs for Kotlin users. The by-ViewModel is delegate function, or the composable function ViewModel. But behind the scenes, those APIs are essentially creating a ViewModel provider for you and getting the ViewModel instance from the ViewModel store. We will not discuss the whole ViewModel provider, but a simplified and short version of it. The first thing to discuss is the constructor, which takes in a ViewModel store a factor and a creation extra. The ViewModel store will retain instances of ViewModels. If there is a configuration change, the ViewModel store will be retained. The factory will be responsible for creating a ViewModel if there are no retained instances. The creation extra will allow you to pass arguments to the factory and construct a customized version of a ViewModel. The get function is the main API and is responsible for orchestrating the communication between the ViewModel store and the factory. When gets called, it will check if there is an instance of that ViewModel in the ViewModel store. If yes, it's going to return that instance of the ViewModel. If no, it will use the factory to create a new instance. It's going to take this new instance, put in the ViewModel store, and then return it. The factory interface is responsible for creating a new ViewModel instance. It takes in a model class that is used to identify what instance will be created, and an extra for additional customization. There are two default implementations of the factory. One is the new instance factory, which creates instance using the noargs constructor. Another is the Android ViewModel factory, which extends new instance factory and adds support to constructors with the android.app.application argument. Last, there is a companion object that includes utilities to be used by the ViewModel provider. So let's start with the constructor. If we look closely, it has a default empty creation extra, and it is annotated with JVM overloads for Java interoperability. Assuming the function parameters are already converted to KMP, we should be able to move the constructor from Android main to common main inside an expected declaration, right? To be sure naught has changed, we can validate the public API. You can do that on the AndroidX repo using MetaLava by running the command gradle check API. If anything has changed, this task will tell us exactly what changed. Well, it seems something has indeed changed. A constructor with 3 arguments has been removed, a new constructor with exactly arguments has been added. If we look closely, there used to be an optional key in the last parameter, but that has disappeared. Let's decompile the Java bytecode before and after this change and compare the outputs. Right, we used to have 3 constructors method. The first 2 is what we expect for Java interoperability when annotating a constructor with JVM overloads. But there is a third synthetic constructor, which is public and has an additional last parameter, the full constructor marker. It seems that it doesn't exist anymore in the decompiled Java bytecode. And because that's a public constructor, change that could cause a compatibility issue. So, what can we do instead? We can leave the constructor for Android clients and write a new factory function for KMP clients, matching the same signature. We do that by introducing a new create function that will be available on KMP and delegating the call to the original constructor. Android clients can still use the constructor, maintaining backward compatibility. KMP clients, though, can use the new create method instead. The first learning is that moving code from Android main to common main may affect your public API. Ideally, you should have an API validator integrated in your libraries project to catch those unintentional changes. Next, the get method. As explained before, the get method orchestrates the creation of view models by using a view model store and a factory. The get method takes in a key string and a model class. If we check the model class parameter, it is a java.lang.class. And as the name suggests, this is a specific Java type that is not available in KMP. We will need to handle that ourselves. We can introduce a new overload that takes in a key class instead, and redirect the call between the 2 methods for backward compatibility. Well, after doing the change we did, we received reports where tests mocking the ViewModel provider class stopped working. Now that mock libraries are not able to differentiate between the 2 get methods. The learning here is simple, don't use mocks. Next, the factory interface. It is a simple interface with a created method. Similar to our previous case, the model class here is a java.lang.class. We will need to handle that too. The solution is similar. We will introduce a new create method that takes in a key class and keeps the class for binary compatibility for Android clients. The learning here is that Java types in a public API might be challenged to change without breaking compatibility. You may need to duplicate or find other alternatives to maintain binary compatibility. The new instance factory is one of the default implementations of the factory interface. If we expand its content, we can see that the implementation will use the model class to get the declared constructor and call new instance. That's how we invoke the noargs constructor of a view model, and that is reflection. Unfortunately, that is not available on all platforms without adding a new dependence to our library. That is Kotlin.full.reflect. But Kotlin full reflect is a large dependence for our lightweight library Lifecycle. The learning here is not all APIs are worth of implementation in all platforms. It's fine to reconsider features that may introduce performance issues, increase binary size, or other issues when converting to KMP. Next, the Android ViewModel factor. If we also expand the content, we can see it takes in a android.app.application type in its constructor that is not available on our platform. Similar to our previous learning, not everything has to be commonized. It's fine to not commonize all the API of a library. In our example, a type like Android ViewModel factory would not make sense outside of the Android platform. Now, let's use the expect and actual keywords to convert ViewModel provider to KMP. That can be done by adding the expect keyword in the command source and provide specific platform implementations that will be annotated with the actual keyword and hold the actual implementation. As discussed previously, we will be converting the get method, the factory interface, and the companion object to KMP. The rest will be Android-only APIs. Because the get method logic doesn't change according to the platform, we could use a default implementation that is shared between platforms, right? Not really. Default implementations are not supported in expected declarations yet. If we count the number of ViewModel providers implementations in the AndroidX repo, you will find 3. Desktop, Android, and non-JVM. We really don't want to duplicate the logic 3 times. So what can we do instead? In the actual implementation for Android, we can extract a new class that will hold the behavior and the state. The new class is an internal type called ViewModelProvideImpl. Each platform will create an instance, and will forward any call to its public API to the internal instance. The new ViewModelProvideImpl now has all the behavior and the state that will be shared by all platforms. But if you remember from the previous slide, we did change the create method from the factory interface to take in a key class instead. That made us change slightly the implementation to accommodate the new create method. And by doing that, we reverted a 2-year-old fix to an issue related to the sugaring for compile-only dependence in libraries. In other words, we crashed popular libraries such as Lee Canary. So let's fix that. Instead of calling the create method directly, let's introduce a new function. The new function is called createViewModel and takes in the factory, the model class, and the creation extra. The function, however, will be an expect function. In all other platforms, we will simply call the create method from the factory. However, for Android, we will backport the previous fix. Because the actual function is now placed in the Android target, we can now access the java.lang.class like before. The idea here is simple. We will first call the create method that takes in the key class and an extra. If that doesn't work, we will call the next create method that takes in a Java class and an extra. If that doesn't work either, we will now call the create method that takes a Java class and uses the default empty extra. In other words, what we are doing here now is we have multiple implementations of the ViewModel provider per platform. We have a shared ViewModel provider implementation that is shared across all platforms. And again, we have multiple implementations of the create ViewModel function per platform target. The learning here is, first, expect class cannot have the full implementations. You will need to handle duplication with other alternatives. Second, the sugaring and minification may cause unexpected side effects, and that might be very tricky to detect. And third, you can mix and match expect actual in methods and classes to reuse as much common code as is necessary. But please note that it may create different behaviors per platform, and you may need to test your code behavior against multiple platforms. The ViewModel class is likely the most used class from the ViewModel library. It is the type that all ViewModel's instances are required to extend from. You won't cover the most simple APIs from the ViewModel. Instead, let's focus on the ones that were a bit challenging to migrate to KMP. One of them is the Closeable APIs. They let you bind the resource to the lifetime of a ViewModel. When the ViewModel is cleared, an associated Closeable will get the call to close method. That allows associated Closeable to clean its resource together with the ViewModel. The add Closeable method can take also a key string that can be used to retrieve the Closeable using the getCloseable method. Next, the ViewModel scope lets you use a coroutine scope pre-configured for UI operations, and it will be cancelled with the ViewModel uncleared. First, let's look at the Closeable API. If you look closely, the Closeable API parameter is a java.io.closeable class that is not available on Kotlin Multiplatform. However, java.io.closeable extends java.io.outCloseable. KMP does provide a Kotlin.outCloseable that is a type alias for java.io.outCloseable, and that we can use here. Because Closeable extends outCloseable, we can change the API signature to take in and out Closeable instead. However, because the first add Closeable has been promoted to stable, we need to ensure binary compatibility by maintaining a add Closeable notation with deprecated and with level set was hidden. That should ensure that any client compiled against an old version of the Lifecycle library would still work if used with a new version. That also means we need to keep an add Closeable variant for JVM only. Now, if we count the number of ViewModel class in the AndroidX repo, we will find two, the JVM and the non-JVM, and we don't want, again, to duplicate the code from the ViewModel. We can use the approach we explored before by extracting the behavior and state to an internal object that will be shared by all platforms. Again, all calls will redirect to the internal type. The new implementation object has all the previous logic and almost everything is KMP compatible. However, the lock mechanism to handle closables is not available on KMP by default. There is a dependence provided by JetBrains called Atomic Foo that has a lock package. But the lock package is experimental even while the Atomic Foo itself is experimental, meaning no ABI guarantees are provided whatsoever. We can't use that in Lifecycle. But what can we do instead? We can implement our own lock mechanism. We will introduce a new synchronized object, a synchronized function that calls an internal expect synchronized implementation function. You might find these two synchronized functions a bit interesting. The reason we need that is because we use contracts to give more information to the compiler when synchronized is invoked. And contracts are not supporting expected functions. So we had to work around that by creating a final function that defines the contract and an internal expect function that holds the actual implementation. Now, for JVM targets, the synchronized object is an empty class and the synchronized method just delegates and calls to the default synchronization implementation. For native targets, however, we need to handle that manually. The synchronized object will be a complex object that will be locked and unlocked when the synchronized is called. We won't cover all the details around implementing a synchronized object, but let's take a brief look at the two implementation details of the class. To implement a synchronized object, we had to use an experimental foreign API. One of the main advantages of KMP is interoperability with native platforms. But that also means you will need to learn to use some of those native APIs. Also, there is a curious expect_vol mutex recursive flag. The reason we need that specific mutex recursive flag is that it has different numeric types depending on the platform. For example, Darwin uses a signed integer, Linux uses an unsigned integer. Now, the ViewModel scope. The ViewModel scope uses the synchronized, get Closeable, and add Closeable APIs we covered before. It returns a Closeable coroutine scope that will cancel when the ViewModel is cleared. And it has a default context based on dispatcher main. The problem here is that dispatcher's main is not available on all platforms. To handle that, we will introduce a new method called createViewModelScope. Different from before, we won't use an expected function, but a single common function. On any platform where dispatcher main exists, we will return it. If we get a not implemented error, for example on Linux, we fall back to empty coroutine context. If we get a legal state exception, for example on desktop swing, we also fall back to empty coroutine context. Finally, we return the Closeable coroutine scope as before. Expect and actual are powerful tools, but not everything needs to use it. Sometimes handling the platform behavior might be fine. We covered many API challenges we faced. Let's take a look into the key takeaways we learned from that experience. First, we strive to find the right balance between the minimal change on the Android versus the best possible common API we can provide for Kotlin Multiplatform. That might not be so obvious when migrating a library, but can be quite challenging. Second, you do not need to reinvent the wheel. Leverage the current knowledge might be enough. When introducing new APIs, try to keep consistency with the APIs you already have in place. Third, Kotlin Multiplatform is very powerful. There has been a few roadblocks, but we also converted a 7-year-old Java API to KMP. That shows how flexible KMP is. Finally, to find out more, why not check out the links in the description? Otherwise, thanks for watching.